So, as you already know, today we're going to talk about how to define and use custom metrics inside NannyML so that you can actually estimate any metric without access to target data immediately after you make the prediction. On the agenda, we have 5 points today. First, we're going to talk about why monitoring realized performance is not enough, why estimating the performance right after predictions made is basically vital to making sure that your models perform well in production. Then we're going to talk about how we can think about and how is it possible to actually estimate custom metrics or generally any metric for regression problems, and we're going to focus on estimating mean squared error or root mean squared error. We're going to stick with MSE here just for the sake of simplicity. And then we're going to talk about how we can extend that to any metric. And here I'm going to give the screen to William, where he will do a bit of a demo where you will see exactly how you can define the metrics and what you need to do to define the metrics inside NannyML so that you can actually estimate it for any regression metric. Then we're going to move on and we're going to talk about how we can estimate any metric, or specifically here, we're going to start with F1 for classification models, and we're going to talk about how is it possible and what's the underlying algorithm. And then finally, we're going to talk about how to extend it from estimating F1 to estimating any metric you want. And again, William is going to give a quick demo here using some, actually, I don't know which ones, custom metrics for a classification model. So let's start with the first part, which is why monitoring realized performance is not enough. And the main reason for that is that models degrade in production. So of course you need to monitor them, but that I'm assuming is already known by most of you. But the second most important thing is that the targets arrive after the damage is done. If you look at the kind of typical timeline of your predictive model, whether you're dealing with automating some kind of work or whether you're trying to predict the future event in the future, the way it normally works is that you get only inputs, then very shortly after the model will make some kind of predictions. Then based on these predictions, hopefully there's going to be some business action that follows. And from that business action, there's going to be some kind of business impact. And then after a while, maybe right after we observe the business impact, maybe even later on, the targets arrive. Imagine that you're trying to, let's say, predict churn. You're doing it 6 months ahead. If you're trying to predict churn of customers 6 months ahead, then the business action will come shortly after the model is predicted, when the retention department is going to try to retain that customer. Hopefully, then the business impact that the customer is retained. And then after 6 months, we will know for sure whether we managed to actually retain the customer or not. So if the model breaks and it will predict incorrectly which customers are likely to churn, we will only know that after 6 months. And that means that the model has been operating already in a very suboptimal state, potentially will fail for 6 months. So we want to catch the model failure as soon as possible, which is right after it makes the predictions. And that is something that we can actually do by estimating model performance based on the data distribution that the model is consuming, so based on so-called covariates. So we'll be taking into account how the distribution changes in time, which is called covariate shift. And based on that, we can actually quantify the impact of that covariate shift on model performance on any metric that you want. And then, of course, we still want to calculate the model performance later on, because estimating model performance is quite good and quite accurate, but it's not perfect. So we still want to make sure that we actually detect model failure that might be due to something else than covariate shift, for example, constant drift. But enough of that. Now, let's talk about how we can actually use metrics. We can then later on define metrics for regression problems to estimate them and to know that something is going wrong with your model early on, right as you make the prediction. So I'm going to start by building a bit of an intuition of how it's even possible to actually kind of predict the model performance. And this is something that's quite unintuitive and definitely not obvious to most people. And that also included me a while ago, where you would assume that if the model is performing as well as it could, so you have this kind of bias optimal regressor here, and you take all the information that you can from the model inputs to predict the target, then if you could predict the model performance, you could use that same information to actually improve the predictions of your model. But interestingly enough, this is actually not the case, and it is possible to estimate model performance even because the information that you're using to estimate model performance is actually not useful for itself. And let's build the intuition here. The way it works is, imagine that you have the simplest possible graph when we are trying to predict a regression value y using just one feature x. And we see that as that feature x increases, the value of feature y also increases. So we can create a model, let's say a linear regression here, because we see that the relationship is linear, and we build basically an optimal predictor. But what we can also see that if we are in the range between 0 and 2, let's say, then we see much higher level of noise compared to the region between 8 and 10. So just looking at this graph, we can already see that if we have a lot of data points in the region between 0 and 2, we would expect to see a higher squared error or absolute error. And we can actually leverage that intuition to try to estimate model performance for regression models. And just to kind of prove that this intuition is more than just an intuition, it's actually something that we can work with. I plotted here the rolling mean error. I think I used absolute error here for a window size of 100 points rolling from left side to the right side of feature x. And we see that indeed this error decreases roughly linearly as the value of x increases. So we can actually use the value of feature x to predict model error, which for regression metrics is basically model performance. And now let's look how we can then basically use that idea that we can train that model that will predict the model error, absolute error, or squared error, and how we can actually train this kind of loss estimation model that we can then use to estimate model performance later on in production without access to targets. The algorithm is called DLE, which stands for direct loss estimation. And the way it works is that we're going to take the model inputs. So in that case, it will be the feature x. And we're also going to take the model predictions. And we're going to treat model predictions basically as a very interesting way to reduce the dimensionality of our model inputs. And we saw empirically that it actually improves the results of DLE. So we're also taking those. And then we're going to train a new model. We're training an LGPM on the test set data. So it's important that we're not using overfitted predictions. We're using predictions that the model makes on unseen data. And then what we're actually going to predict with that new model that we're training is the loss, however we define it. So we'll be able to define it in any way we want. But for this example, let's say that our loss is the squared error. So we're going to try to predict the squared error of the model for every data point in the test set, for which we have known truth, using model inputs and model predictions, which we also have. Once we've trained that model, then we can visualize this estimated loss landscape. We see the test distribution, and we see what is the expected squared error that the model has learned based on where data points lie in the model input space. And once we see the current new data, we deploy the model to production, and we try to estimate model performance on the production, we will basically do the exact same thing where we're going to try to predict using that LGVM that we train on our test set. We're going to then predict for every data point in the current channel of data, let's say current week of data, or current day of data, or hour, or 10,000 data points, however we want to aggregate our predictions to get the prediction that is believable. We're going to then, for each of those data points, predict squared error, and then we're going to take some kind of average over that, let's say mean, and we get our mean squared error that we can estimate on the current chunk of data without access to targets. This is the kind of quick overview of how it works. And then just to visualize how it will actually work. So we're going to have these chunks of data in time. And as we basically see these data points coming in, we want to have enough data that we can actually estimate it in a believable way. And if we see that there is an increase of that over time or compared to the test set, we can trigger an alert, an error, and you know that your model performance is no longer as it should be within the specified range that you saw on the test set. Quick results here, something that I always want to point out. It's not the focus of this webinar, but one interesting and I think quite impactful insight is that we cannot use drift detection methods, even multivariable detection methods, to reliably detect changes in model performance, because the data can actually drift to regions, and it can be a very significant drift, but data can drift to regions when the estimated error is roughly the same as the current regions, which means that even if we observe very strong drift, like we observe here using our PCA reconstruction error method that detects multivariate drift, we still don't see a very strong increase in this case, MAE, so in the mean absolute error. And now let's talk about how we can actually use custom metrics and define any metrics, and how we can then use DLE to actually take that metric and estimate it without access to target data. And the way it works is basically we need to define two functions. We need to define our loss function that's going to take the actual predictions. It's going to take the true value, so the actual target data, the targets. And we can also use any data that is in the chunk. So we can use the segment values, we can use the timestamps, so we can have some kind of exponentially decaying metric if we're interested in that. We can have metrics that are weighted by segment, or we can have any additional data there that we are interested in. Typical loss functions will be the absolute error, squared error, or the logarithmic error, or the regression models. And then once we have that instance level for every prediction, we're going to define that loss, and we're going to be able to predict it. Then after we have these predictions, as I already mentioned, we're going to aggregate them with taking the mean, taking the root mean or RMSE, maybe the median or the maximum. There's also a few metrics that use, for example, median absolute error. I think is a metric that is used in some niche use cases, so that's something that you could do. And if I believe correctly, now is the time for me to hand it off to William to do a quick demo. So William, go ahead.
All right. So before we delve into the NannyML cloud product, let's first quickly brief where we can find it. So we can either find it on the AWS marketplace. You can just search for NannyML, and then there is a CloudFormation template that you can use, or a Helm chart deployment that you can use. And it all comes with a 1-month free trial. So if you want to try out whether you can estimate the metrics that you're currently using, but that are not that popular, maybe in scikit-learn and not supported by default by NannyML, and you want to try it on your own data, you can just spin up the NannyML cloud trial. It will take around 30 minutes, and then you can try it out on your own data. And you can also find it on the Azure marketplace, where you can search for NannyML as well. And then you can pick the managed application, which is basically similarly to how we deploy on AWS, where NannyML gets deployed inside of your cloud environment, so that there is no data being sent to us, but that all the processing happens within your environment. And after that's done, then we enter NannyML Cloud, and this is the monitoring hub, where we have a collection of all of our machine learning models in production. And as you can see, there's already lots of models there. These are Kaggle data sets. And before we're going to be adding our custom metrics, I'll first quickly show you how to add a new machine learning model. And we're going to be taking a data set where we're going to predict the tip amount people leave after taking a taxi ride. So the problem is going to be a regression problem, and we want our metrics to be aggregated daily. And we're going to call it tip amount prediction. And then we need to provide some reference data to NannyML. This is typically the test set. And we're going to take this data set here and then upload it. And NannyML will use this test set to extract baseline model performance, to extract distributions, for which we can then compare our data in production against. And we need to provide some small things, configuration for NannyML to understand this data. We need to select the timestamp column. Some other fields are already automatically extracted by NannyML, and we need to also say to NannyML what the target is, and that is the tip amount right here. If we want segments, we can provide here a segmentation column as well, and then also the custom metrics will be measured per segment too. And there is also something else. What we can do is we can decide to ignore certain columns. And why is that important? That's important because that means that we can provide extra information to NannyML that might be related to the custom metric, but that we don't necessarily want to track as part of the other monitoring that we do. And it's just extra information that we can add to this data, and then decide to ignore as part of monitoring, but leverage during the calculations of the custom metric. And then what we need to do next is go and fetch the monitoring data. And here we just can select the analysis data that's already there. So this is basically all the predictions that we've made for these taxi rides and how much the tip is going to be after the model has been deployed into production. And in this case, we also already have the target data, so we can supply that as well. And then there is one small field where we can configure all of the things that we want to calculate, estimate, like drift metrics, concept drift, data quality stuff. But since we're focusing mostly on performance metrics, if we had already defined a custom metric, we could have added here right now. But since we haven't done that yet, I'm first going to add this data and run it. And then NannyML is going to be crunching some numbers. And while we're waiting for these numbers to be crunched, I can start adding a custom metric. But let me first see if the run starts, because that will give me an idea whether I did the configuration correctly. And there we go. So NannyML started crunching the numbers. That means that we can define a custom metric. And how that works is that this is basically a collection of all the metrics according to what type of machine learning problem we're solving, whether it's binary classification, multi-class, or regression. And we can just add our metrics here, and then we can later connect them to whatever use case we have running in production. So this is basically a collection of the metric definitions. And the reason why there is why they are different across these three types of problems is because NannyML does different types of calculations under the hood according to what problem it is. And since this is a regression problem, I'm going to add a new metric here, and I'm going to copy some code here from this notebook, where we're going to take pinball loss, which is basically a type of loss, also sometimes called quantile loss. It's a metric where this is just a visualization of the loss metric. But what it basically does, if we take low values for the alpha, we make overprediction more expensive, and then the model is incentivized to underpredict the targets. And for instance, for this use case, since we're predicting tip, we are going to set this pinball loss to be very small, so that the model is actually incentivized to underpredict, so that maybe more people actually are seen to be a lower tip, so that then we can incentivize them during the ride to potentially leave a higher tip. And we need to fill in some fields here. So we say pinball loss with alpha equals to 0, 1 as a description. And then there's two parts to the loss metric, to this metric. Actually, one is the loss and the other one is the aggregation. So the loss is what we calculate at instance level. And this is very simple for this metric. And there's two definitions. And then after that, we just basically measure the instance loss and then we aggregate it. And that is just here, mean, that where we take the mean per chunk. So in this case, that's going to be the mean of this loss per day. And we also have the chunk data here. And if we had supplied more data to NannyML, we could, and we potentially would have said that these columns were ignored, we can access that data here inside of this object, and then we can do whatever calculation we want with it. This might be prices or some information from business, or some extra weights to make a weighted metric. And also all the features and the other elements are accessible in the chunk data, like Wojtek said. Also the time component is there. So if you want to make this metric change over time, that's also possible. So I'm just going to copy these two and then add them to the metric definitions. And then we can save this metric. Does not contain. Did I copy that? I didn't copy it properly. There we go. Yeah, that's it. And now this metric is basically accessible for all the models that we have in production. And we can actually also see here by which models this metrics is being used. But since we haven't defined the connections yet, there's none of these models available yet. So we're just going to go to our tip amount prediction and add this metric. By the way, we put mean absolute error actually as the main metric, where we can see here the performance on the test set. The model gets deployed here, and then we see this performance metric in production, and we see here in the last few days that there is an actual issue with this model in production. And what we can do now is actually in the settings under performance metrics, we can add our custom metric, which is the pinball metric that we just defined, the pinball loss. and then add it, and we'll have to rerun some of the results here. So that's going to take a few seconds. And then this metric is going to be available inside of the performance dashboard, where we right now have our standard metrics as part of the default settings. But as soon as this finish running in a second, we'll also actually have the pinball loss there. And now we can go to performance again. And then we have our little metric here. And then we can see both, because we provided the target data, we can see the actual real performance where we compare the targets and the actual predictions. And we can also see the estimated performance where we don't leverage the target data at all. So ideal when the target data is delayed or not accessible at all. And we see here actually that we're directionally correct. We can actually compare both how these looks. We're directionally correct, but not fully. And that's because in this data set, there's also some concept drift happening, and the concept drift is not encaptured with this algorithm because this algorithm actually quantifies the impact of covariance shift on the performance metric. So if you would do further investigation, we would be able to explain this gap by some concept drift that's happening. But at least right now we see how we can add our own custom metric and how it can be quickly added to NannyML, and that we can calculate it and then actually also estimate it. And then Wojtek, I'll give it back to you so that we can do classification.
All right. You should be able to see my application. Also, let me know if you can hear me better now. If it's fine, Wiljan, you can just confirm that you can hear me better now.
I can hear you, but I would say it's marginally better. It's almost the same.
How about now?
I think this actually might be a little bit better, to be honest.
Maybe it is actually just my microphone. Okay, perfect, cool. So sorry for the interruption, and now let's move on to classification. So we're gonna now talk about custom classification metrics, and we're gonna explain in a very simple way the algorithm that we use called CBP to estimate F1. And again, I'm going to start by building the intuition. How is it possible to actually predict or estimate model performance without access to ground truth? We already know from the regression metric idea that it is actually possible, because basically estimating the variance in the data or the uncertainty of the prediction is not necessarily related to the actual prediction value, but it's kind of an orthogonal problem. So what we're going to do is we're going to leverage the same intuition here. But instead of training a new model from scratch that will try to estimate this uncertainty and this variance in the data, we're going to use the predicted probability as a measure of uncertainty. And then at some point, we're going to also calibrate it to make sure that it's a reliable measure of uncertainty. And the way we do it is we're going to start with the actual prediction, so predicted probabilities, and then I'm going to define a confidence measure, which is basically how close the prediction is either to 0 or to 1. So if a model is very confidently predicting that a data point is going to be a positive class or a negative class, then I'm going to say it's very confident and the prediction is close to 1. If the model prediction is close to 0.5, then we're going to say that the model is not confident, and we're going to assign the confidence score of 0 to it. And here we can see a very simple XOR problem where we have two classes, and we build a nonlinear SVM function that tries to predict whether a data point belongs to a positive or to a negative class. And we see this kind of beautiful dragon fruit picture of model confidence as a function of feature 1 and feature 2, feature 0 and feature 1 actually. And now if we look at the test data, production data, we're going to use the idea of covariance shift, so change in the model distribution, to try to quantify what is the expected level of performance on that chunk of data, that production data. And here we see that the data can actually drift to regions that are more uncertain. For example, much closer to the class boundary. And here we see an extreme example of that, where most of the data actually drifts towards 0, 0 point, which is extremely uncertain because we have absolutely no clue whether the models are going to belong to class 0 or class 1 there due to a bit of noise. So if we see that most of our data points are in very uncertain regions, then we're going to say, at least based on that, based on visual inspection, in a while we'll learn how to actually quantify that, but we can already say that we expect model performance to drop due to this shift towards uncertain regions. And the way we can do it actually is we're going to try to estimate for each data point again. So we're going to use this idea of first we're going to, for every instance, so we're going to do an instance level performance estimation, and then we're going to aggregate those instances in a certain way to get an actual metric that we are interested in. So let's start with the actual confusion matrix. I'm going to be using binary classification here as an example, but the same exact algorithm actually works for multi-class, just the engineering implementation is different. That's why we were different metric definition. Without further ado, we have our confusion matrix and we get our prediction, which happens to be 1. The first prediction is 1. What do we know from that? We already know that the prediction is not going to be negative because it's being defined as positive. Model outputs the positive prediction. So we can already say something about the confusion matrix. We can already put both in the false positive, false negative, and true negative cells 0. But we still don't know whether it's going to be a true positive or a false positive. Luckily, we also have access to predicted probabilities. And for the time being, we assume that these predicted probabilities is something we can trust. We can say that this predicted probability is actually well calibrated, which means that it conforms to the definition of frequency, definition of probability. So if we get 1,000 or let's say million predictions that predict 1 and have probability exactly 0.7, then roughly 70% of them would actually turn out to be positive. If that's the case, then we can actually assign in expectation 0.7 to the true positive cell and 0.3 to the false negative cell. And if we get enough of the data points in a given chunk, then we can actually reasonably well trust our estimations. That's why we actually also need to aggregate the predictions into a bigger chunk to make sure that this level of noise that has to do with only using expectations and not real value kind of washes out and cancels itself. So then we can use basically any metric that we want. For example, F1, which actually uses the wrong definition here. So we do ignore what it actually says here. This was supposed to be accuracy, but yes, it would be estimated accuracy here, and we just take the true positives, true negatives over everything we have, which is just 2 data points, and we get 0.65 of estimated accuracy. But we actually cannot trust these predicted probabilities because the predicted probabilities that your model learns, whether it's a gradient boosting model, whether it's a deep learning algorithm, whether it's maybe, what else do we have there? Basically, SVM, linear regression, logistic regression, whatever you use, you can actually fully trust these predicted probabilities with potential exception of logistic regression. So we need to calibrate them. What is calibration? Calibration, in a nutshell, is making sure that the observed fraction of positives that we see in the test set matches the mean predicted probability for either a subset of our data set or the full data set. And to make it useful, we're going to actually divide our probabilities on the test set or predictions into buckets, where we're going to aggregate all the predictions between, let's say, 0 and 0.1 predicted probability into one bucket, and then we're going to do the same into 10 different buckets. Once we have those buckets that you see on the x-axis, we're going to observe what is the realized fraction of positives on the y-axis here. So if the mean predicted probability of all the data points that predict between 0.1 and 0.2 is, let's say, 0.17, if these probabilities were well calibrated, we would expect to see 17% fraction of positives, so 17% positives in that specific bucket of data. But for most of the example models here, this is just a screenshot from scikit-learn, we see that it actually does not follow the straight line we would expect it to follow if the model was well calibrated. So what we're going to do is we're going to fit a one-dimensional regression model that will basically map the classifier's predicted probability to the correct fraction of positives. And we're going to do it for every instance. So we're going to take the classifier's predicted probability as a feature, and then we're going to take the actual prediction as the output, as a target. And once we've trained that classifier, and we're going to train the classifier on the test set again, avoid using overfitted data to train it. So it's a regressor. Then we can actually trust these estimated target probabilities or calibrated predictions, as they are also called. So let's say that we calibrated those probabilities for the first prediction instead of 0.7, now we're getting 0.6. So we're going to adjust the metric based on that, and we're going to also adjust the confusion matrix. And we can then fully trust our predictions with two caveats that are actually quite important, that it works only on the average for the entire reference set, and it only fully works for the reference covariance distribution. So we actually see a strong covariance shift. This calibration might not hold, and this is something that we actually already solved with another algorithm that is called Bake. But we don't have the time in this webinar to explain how that algorithm works. But I think William is going to show how it works in practice, so you will see that it captures even stronger covariance shifts. But before we go into that, another example of why using multivariate drift detection methods is not the way to go to estimate or to find signals for dropping performance. And here we see a kind of inverse idea that even if we see no strong multivariate drift, we still might observe significant drop in model performance. That is something that we should be worried about, because even if drifts are small, if we see that strong changes in expected model performance, because for example, we're getting close to the class boundary, the model performance can basically crater very fast, even if we see small drift, which might not be captured by the method that we're using to detect data drift. Now, the last part of the webinar, so how we can then extend this idea of estimating actually accuracy to any metric. And let's talk about, again, what are the things that we need to provide. So here, both to estimate and to calculate a custom metric, we need to provide the column that has the targets. And again, of course, we only need the targets for either computing the performance, the actual performance that we get, or for fitting the calibrator on the reference data. We also need the column for predictions, the predicted probabilities, and information of the chunk data if we want to use it at all. And then for estimating the model, we're going to do a very similar function, but instead of using the actual targets, we're going to use estimated target probabilities, because that is something that we need to run our CBP algorithm or the improvement of that, which is called PAPE. And now, again, I'm going to give the screen to William to show how it actually works.
Right. So when I explained regression metrics, I did everything via the user interface of the product. And right now I'm going to leverage the SDK to do the exact same thing, but for classification. So the first thing we need to do is, of course, import the NannyML Cloud SDK and then connect to the actual instance that would be running in your cloud, which is just a URL. And then you can create inside of the application, you can create a little token here. And that way you can connect this notebook and the settings to your monitoring instance. And the first thing that we need to do, same thing as last time, is to fetch some reference data and load that up. This is a hotel booking data set where every line is a customer, and we're trying to predict whether they will cancel their booking in the next 3 months. It's a Kaggle data set. And in this specific setup, we have lots of features about the problem, and this is the reference data, so the test set. So we actually also have the target available, whether the customers ended up canceling their booking. Then we deploy the machine learning model, and we have a look at the analysis data. So basically all the predictions that were being made after the model was deployed. And in this case, we don't have the target data yet, because we will only know in 3 months whether these customers actually ended up canceling their booking or not. So this target data is not available yet. And then what we need to do is the exact same thing as last time, do a little bit of a schema setup where we do the mapping of these columns contain the target, these column contains the predictions. Maybe there's a column that I want to segment on, or some columns that I want to ignore because they contain information that we want to leverage inside of the custom metric, but not necessarily as part of the other things that we're monitoring. We give the model a name, and then we say, okay, in this case, we're actually interested in aggregating the metric on a monthly basis, and our main metric of choice is going to be accuracy. And then if we run this, NannyML is going to I ran this already when Wojtek was explaining classification. So we can already have a quick look at this use case and the main performance metric, where you can clearly see here would be the real accuracy. So the actual accuracy measured, we're leveraging the model output and the targets. But since there's no targets available, we only have the accuracy on the test set. And then here, when we deploy, we're basically in the blind and we have no view on the actual model performance post-production. But since we have our algorithms, we can estimate model performance at the moment of inference time. And that way we can already create a view on the expected performance while we're waiting for the target data to come in. And what we're going to do right now is we're going to use this SDK to define a custom metric and then add it to this model. And for classification, it's a little bit different. So it's not defining a loss function and then aggregating. It's basically separating between calculating, so to measure the real performance, and then estimating the actual expected performance. And here we're going to do the F2 score, which is just a very small variation on the F beta score, where we're just going to use the scikit-learns implementation and define a beta of 2 to measure the real performance. And I've added a few lines here to tell how this metric to behave when the target data is not available yet. So this is basically measuring, okay, if there is missing data in the model predictions, we're just gonna return a missing value for this metric, which makes sense because there is no target data, so you cannot actually measure the F2 score. And I'm gonna run this. And then for estimating, it's gonna be a little bit different. There are still things we need to define in terms of what contains the predictions and the probabilities and the chunk data that we leverage, but there's something else, which is the estimated target probabilities. And this is something that Wojtek explained, where he basically showed this confusion matrix. And all these expected confusion or these expected probabilities, they are present inside of this object. And then we're going to leverage those to first get these expected confusion matrix elements. And then we're going to actually estimate the F beta score using these expectations. But it's very important to know that if you would measure this, you would not use the expected, but you would actually use the real true positives or the real false positives. And right now we're just basically leveraging the probabilities and then the confusion matrix elements. And that's all there is to it. And then what we can do is we can define a metric using the SDK, where we give it a name and a small description. And again, these two functions, we pass them along, and then they will be sent to NannyML. And we're going to be able to find them after I send them as part of the custom metrics. Here we see right now that this metric appeared there. And then the next thing to do is that we connect this metric to an actual model. And that's going to be this model that we just uploaded, the hotel booking prediction. And then we can trigger also from the SDK a new monitoring run that's going to get executed. And then if I go to monitoring and to the actual use case, we're going to see that NannyML is already crunching this new metric. And when it's done running, it's going to be available again underneath the performance tab, where we can delve in deeper and have a look at this metric. So right now the run is complete. And let's first look at the estimated performance, because of course we don't have target data yet. And then we can look here at our custom metric and we see that it's actually fairly stable in production. But remember that when we had a look at accuracy, the expected performance was dropping. And right now we could also compare both realized and estimate. But of course, since we don't have the target data yet, this metric is not actually further available in production. So what we're going to do is we're going to send some target data, and then we can actually see how well we did at estimating these metrics post-deployment. And the way we do that is we just send the actual customer IDs and then the actual outcome, whether they ended up canceling their booking 3 months later down the line. And we send this target data to the actual model, and that's it. Very simple. And then we can come back here and then quickly refresh and see whether this run is almost executed. And we can already see here right now that the target data for the main performance metric came in and that we can measure the real performance. And we can actually see that we're pretty accurate at estimating this model performance. And that's also because specifically for this use case, most of the performance deterioration is caused by covariate shift. And that is exactly what we're trying to pick up with these algorithms, to quantify the impact of the covariate shift on the performance. And since this run has finished right now, we could go back to our main view on our custom metric, and we can see here how well we did at estimating this accuracy metric. And we can see that, first of all, we might miss out on this little bump here, but this might be actually completely random because it's falling between our expected performance thresholds. So from this perspective for our custom metric here, there's nothing to worry about. But we can see here that from an accuracy perspective, there's something that we might want to do to delve deeper and have a more deeper look at what actually went wrong with this use case. And that way, we've actually wrapped up of both how to add a regression metric and a custom metric for binary classification. For regression, we both do the loss and the aggregation, and for binary classification, we do the calculation and the estimation. Maybe a small thing to add here is that there is a possibility to define lower bounds and upper bounds. And for instance, what we might want to do for ROC AUC, if we know the metric should lie between 0 and 1, we can put in these bounds so that when there's lots of variability on the metric on the test set, it might be that the actual performance thresholds that are extracted automatically fall above 1. And if you define these bounds, then this upper threshold is not going to be displayed on the visualizations, and that's going to make it look a little bit neater. And that's it for the demo part.
All right, then it's time for me to go back. I hope again that you hear me a bit better, but even if you don't, fear not, because we're almost done. So, summary, we have 3 points here. First one is that the estimating model performance is the only way to detect failures before business impact. So this is the only way that we can actually figure out that something is going wrong with reliability without we get actual business impact. And this is something that's quite unique to NannyML. And as far as I know, we are the only product company, open source library, whatever you call it, that provides that solution. And then secondly, for classification metrics to define a class or for any problem that can be expressed as a classification problem, we need to provide a computation definition, an estimation definition or estimation function. And for regression metrics, just for basically any regression loss that you're defining, we need to provide the loss function and the aggregation function.